Many methods for statistical inference require assumptions about the probability distribution and associated parameters of the population, such as the normal distribution with population mean and standard deviation as its parameters. These methods are called parametric methods. And in contrast, there is also a group of inferential methods that do not assume that the population distribution has a particular form. And these are called non-parametric methods, or alternatively distribution-free methods. In this video, I'll explain when it's wise to use non-parametric methods. Let's start with an example. Imagine tomorrow is your birthday and you have decided to give your friends and yourself a special treat on this occasion. So you go to the local confectioner to buy 7 pastries. The choice is overwhelming and everything is delicious anyway. So you ask the confectioner to select 7 pieces of pastry at random. You can consider all the pastries available in the shop as the population, and the 7 pieces are a sample from that population. Now, each type of pastry is priced differently, and it is the price that we will consider as the variable of interest here. In this graph, the probability distribution for the prices of all the available pastries in the shop is given. It's the population distribution. And down there, you see the prices for the pastries that the confectioner selected for you. Now you could, on the basis of your sample, estimate the mean price of pastries in the shop with a confidence interval. Or you could test whether the confectioner has given you pastries that are a bit at the expensive side, if you knew the amounts and prices of all the pastries in the shop and then calculate the population mean. The standard probability distribution available to answer these questions would be the t-distribution. However, it makes a number of assumptions that are not exactly met. First of all, the population is not normally distributed, but it appears to be skewed towards the left. Secondly, the price range is limited. It does not exceed the value of 6 and is never lower than 1. So what happens by still applying the t-distribution to calculate, for instance, a confidence interval? The confidence interval can still be calculated, and it would suggest that in 95% of the cases the estimated range would contain the true mean. But in reality, this confidence interval would probably be overly optimistic, and would in this case in fact contain only the true mean in 90% of the cases. We could check this by repeating the sampling of 7 pieces of pastry 100 times. It would then, in only around 90 cases, lead to a confidence interval which contains the true mean. So, by applying a parametric approach to calculate a confidence interval, or a hypothesis test, while the assumptions are violated, the numbers that you get become less accurate and may in some extreme cases even be very wrong. Obviously, you would like to avoid making such errors, and that's why you would always try to apply an analysis method for which the assumptions are met. So if you know that the assumptions of a parametric test are violated, but that there is a non-parametric equivalent test available for which the assumptions are met, you would choose the latter. Another important reason to use a non-parametric technique may be a limited sample size. When you have just a handful of observations, say less than 15, violations of the assumptions in a parametric test are particularly hard to detect. Yet, such a violation can have large effect under these small sample conditions. In general, non-parametric methods make less assumptions than parametric methods, and can therefore be applied more frequently. But that's not the only reason why non-parametric methods are useful. An even more important reason may be related to the measurement level at which the data is available. A lot of data has an ordinal measurement level. For ordinal data, with for example 5 incremental classes, you cannot calculate a mean and standard deviation in a meaningful way. So for that type of data, you cannot apply a t-test, an ANOVA, or calculate a Pearson correlation coefficient. Fortunately, there are many non-parametric methods that don't work with numerical data, but are specifically designed for ordinal data instead, the so-called rank-based methods. With these rank-based methods, you can, for example, compare the estimated median based on a sample against the theoretical median, and also calculate the correlation coefficient amongst 2 ordinal variables. Typically, these rank-based methods are insensitive to outliers in the data. And that brings us to the next property of non-parametric techniques. If some assumptions for non-parametric techniques are not met, they are usually fairly robust to these violations. This means that the reported confidence intervals or significance may not be very accurate, but it won't be far off the real value. For most parametric tests, there is an equivalent non-parametric test. If it's not testing exactly the same population parameter, then it is testing a parameter that is equivalent in practice. The two-sample t-test, for example, tests for a difference among two sample means. And there's a corresponding non-parametric test which can test for a difference in two sample medians. The underlying question usually is whether the two samples come from the same population, and that question may be answered by testing for a difference in means as well as medians. The downside of non-parametric methods is that their power is usually lower than that of the equivalent parametric test, if the assumptions are met. This means that you would need more observations or a larger effect size to correctly reject the null hypothesis with the non-parametric test. And for that reason, parametric tests are often preferred if the assumptions are met. Let me try to summarize. Non-parametric methods are advantageous in 4 situations. First, the underlying probability distribution may be unknown or known to be different from what a parametric method requires. Second, the sample size may be very small so that it's impossible to test whether parametric assumptions are met, while violation of these assumptions may have severe effects. Third, the measurement level may fall below what is required for a parametric technique. And finally, there may be no parametric technique available at all for the specific question at hand. In general, a non-parametric method is more robust than its parametric equivalent. Robustness means that when assumptions are violated, it doesn't heavily influence the outcome of the test. However, the power of a parametric test is always higher than an equivalent non-parametric test, and therefore, if there is a choice and assumptions are met, a parametric test is preferred.